Okay, hello, thank you for joining us and welcome to Raycastle's live webinar looking at the digital railway supported by Frmcs. Before we get started, if I could ask you all to mute your microphones, that'll just prevent a little bit of background noise. Thank you. So in this webinar, we'll discuss the main features of the future railway mobile communication system, how it differs from GSM-R, the migration strategy, spectrum issues, and the probable technologies that will be deployed. The webinar will be delivered by Les Granfield. Les is a technical trainer with over 35 years of experience. His expertise extends across a wide range of technologies. He specializes in GSM, GSM-R, ERMTS, UMTS, LTO radio access, radio planning, network optimization, and push to talk over cellular. Okay, if I could have the next slide, please, Les. First, before we get going, a brief introduction to Raycastle for those not familiar with us. We're founded in 1958. We initially specialized in radio and maritime communications. We began training the telecoms industry during the 1990s and have established ourselves as the leading training organization in this field. We have an extensive portfolio coverage covering all the major telecoms technologies. We use a variety of delivery formats, from classroom to live virtual classrooms, such as this session, and on-demand distance learning. And during the past 60 years, we've trained over 300,000 industry professionals from across the world, with a preferred partner for many telecoms industry giants, and you'll see really just a handful of those there. So what's new at Raycastle? Well, we're recently acquired and are under new management, so there's been lots of new names around the business. During the last 12 months, we've launched a new Enterprise Online Academy, providing access to all of our learning pathways to all employees within an organization. We've expanded internationally, including the sale of our first academy to mobile operation in Asia. We've launched a new consulting division. We've introduced a mini MBA in telecoms, extending our training reach to cover the business of telecoms, including management, leadership, and business model development. All our courses are also now available to purchase online, giving you immediate access to our on-demand training courses. If you'd like to find more about us and our training courses, please visit our website at raycastle.com. Here you'll see, next slide, you'll see key members of the management team and the training team. If you'd like to contact any of us, please drop us an email at info@raycastle.com and we'll be happy to get back to you. Before we get on to the main presentation, just a little bit of housekeeping. The presentation will last about 45 to 50 minutes. If you have any questions, please post them in the chat box and Les will answer them at the end of the session. So now I'd like to hand over to Les for the main presentation. Les?
Thank you, Paul. Thank you for the introduction. I'm just having problems with my cursor at the moment for some strange reason. So yes, welcome. Very good morning, very good afternoon, wherever you're located. And this is the digital railway supported by Frmcs. And we start by just illustrating an egg timer. The reason for the egg timer is to make a small point, and that is time is running out for GSM-R. Now, GSM-R was created back in about the year 2000, after some 10 years of development. Its intention was to provide a pan-European radio communication system for the railways across Europe, and that avoided using dissimilar systems in different countries. And it is now widely deployed in many European countries and has been very successful. The technology that we have is based upon a European-funded project called Marine, where Marine stands for the Mobile Radio for Railway Networks in Europe. And the actual current specifications are maintained by both the UIC, the International Union of Railways, and ETSI, the European Telecommunication Standards Institute. The two specifications maintained by the UIC, of course, is the Functional Requirement Specification, the FRS, that describes what the system needs to do, and the System Requirement Specification that describes how the system will actually work. Now, that's actually used in conjunction with the ETSI specifications, which look at the actual GSM specifics. Now, GSM-R was always part of ERTMS. ERTMS is the European Railway Traffic Management System. This is a major project underway in Europe where we're going to replace all of the dissimilar train control systems and have one system across the whole of Europe, and that's known as ETCS, the European Train Control System. So ETCS is all about passing, signaling information to trainers to control the actual movements of those trains. And the way we're going to deliver those instructions is via radio, namely GSM-R. Now, GSM-R is often referred to as a MOTS, where MOTS actually stands for a modified off-the-shelf technology. And the reason for that is because when GSM-R was being conceived, it was felt that rather than actually build a brand new system from scratch, it would be more cost effective to actually use existing commercial GSM components, modify them and make them more sort of railway specific. So it was felt that would have been the economical way to actually build a new network. However, the operators over the years have discovered that the capital expenditure and the operational expenditure of a GSM-R network has proven to be quite high. Now, if you couple that with the fact that the manufacturers intend to cease support for GSM-R in around about 2030. I know one manufacturer sort of quoted 2035. And because ERTMS is expected to support or require support to 2040 and beyond, then clearly if we're going to lose GSM-R, we need a successor. And that successor is in the form of FRMCS, this future railway mobile communications system. Now, FRMCS is not simply a replacement for GSM-R. FRMCS is not even a single technology. It's actually a collection of applications which potentially can actually open the scope for communications within a railway environment. And we'll discover some of those applications in the following slides. Now, the UIC are responsible for the FRMCS project because ultimately it is a project, and that project kicked off back in 2012 when the UIC published a document referred to the User Requirement Specification, the URS. That was published, made available to all interested parties. Feedback from the railway community allowed the UIC to modify the document, and a second version was published in 2016. And then there were a number of iterations of the actual document. And the final version of the document, version 5.0, was published in 2020. What the user requirement specification does, it attempts to capture the communications needs of the railway sector. And having captured the needs of the actual railway sector, what we can then do is create functional use cases. So the UIC have published a functional use case. And the reason for that is because we need the functional use cases, first of all, to provide the standards bodies with material to work on. The standards bodies we're talking about is 3GPP, the third generation partnership project, which of course includes ETSI as well. And they will use those functional use cases to perform a process called gap analysis. Gap analysis is actually looking at the use cases and then identifying which standards already exist that could fulfill those requirements. And then, of course, we can identify which standards need to be developed in order to actually support those functional use cases. So that's a process that's actually ongoing today. The second reason for those functional use cases is they will be required to create the functional requirement specification, the FRS. Now, the functional requirement specification was promised this year, 2021, and we need the FRS so that we can create the system requirement specification, which was also promised this year. And an important milestone is 2022. So next year, by the end of next year, the TSI CCS, that's the technical specification for interoperability, control, command and signaling standards documentation needs to be updated, and it requires the FRS and the SRS for that particular task. So no pressure then. By 2023, there should be an FRMCS demonstrator in position. By 2024, we should see the first national trials being conducted. And then hopefully by 2025, the TSI will be ready and equipment will be ready from the actual manufacturers. So the time frame is quite tight, but I'm confident we will get there. Now, another project that's been set up by the UIC is referred to as 5G Rail. To give it its full title, it's the Horizon 2020 5G Rail. 5G for Future Railway Mobile Communication System. It's a project that kicked off on the 1st of November back in 2020. The project is anticipated to last for 30 months, and a budget of 13 million euros has been set aside for that particular project. As mentioned, we do need to get this sorted out fairly urgently so that we can actually update the CCS TSI by the end of next year. And it needs the FRMCS interoperability functions. So we need to be able to test and validate the specifications, and we're aiming to create the first version of FRMCS. Now, the way that's going to be done is perhaps performing cross-border emulation trials. We need to create functional tests. We need to develop and evaluate the various prototypes for the onboard systems and the trackside systems. And that will include ETCS, European Train Control System, ATO, automatic train operation, voice and video as well. And the anticipated technology is 5G, but more about that point in just a few moments. If you look back in the GSM-R, FRS and SRS documents, it gives you a description of the current standards or services which are available. And we can divide those into voice services, data services, and railway specific services. Now, the voice services include all the familiar ones like point-to-point calls, so a driver can speak directly to a signaller and vice versa. We've got public emergency calls, where, for example, a driver could dial 999 or 112 and set up an emergency call to a public emergency operator. Broadcast calls, where a signaller can actually broadcast a message to all trains in a given area, or perhaps on a station. And group calls are point-to-point call, point-to-multi-point calls. And multi-party calls and conference calls, for example, those are identified as voice services in the current GSM-R standards. The data services include text messages, so we can use SMS texts. We can use GSM to carry general data. It can be circuit switch data, possibly GPRS as well, packet switch data. I've never really understood why you can actually send a fax message to a train driver, but automatic fax messages are also possible. And train control. Train control, of course, would include ETCS, the European Train Control System. The railway-specific services include functional addressing. So that means that the actual signaller doesn't need to know the telephone number of the cab radio. He can use the train running number or the head code of the train to actually set up a call to that particular driver of that particular train. Location-dependent addressing is all about ensuring that a call from, let's say, a train is routed through to the most appropriate signaller in the area where the train is currently located. And of course, we have the special railway emergency calls. So by pressing the big red button on the cab radio, we can initiate an REC. So in total, we've got 12 GSM-R services, just 12 services. Now let's compare that to what we can potentially achieve with FRMCS. Now with FRMCS, we don't talk about services. They're referred to as applications, or more generic term, apps. So these are going to be apps running on a smart device, very much like having a smartphone perhaps. But the applications have been defined in the user requirement specification, the URS, and they're divided into critical communications. Now, critical communications are communications which are supporting critical operations, such as the safe movement of trains. We've got performance communications. Now, we've never seen this perhaps before, But these are a bunch of applications that can be used to enhance or improve the performance of a railway network, such as ensuring trains depart on time. And then business communications. So a set of applications that can support the railway business. So for example, we could charge members of the general public for using a particular service. Now, we also require supporting features. So there's a collection of features which are referred to as critical support features, and they will be there to support the critical communications. And they will involve things such as quality of service, class negotiation, authorization, authentication, arbitration, for example. The performance support features are currently not yet defined in the URS, so we're going to have to wait a little while to see what's actually included in performance support features. And the business support features are also sort of a little bit short on detail, but one which is mentioned in the URS is billing. So let's have a look at the critical communications applications, of which there are 31. The last time I quickly counted them in the URS. And as you can see from the diagram, they're divided also into 3 groups, which are voice, data, and video. Now that's a new one. Now in terms of voice communications, running through them very, very briefly, top to bottom, on train outgoing voice is basically the driver calling the signaller, a point-to-point call. On train incoming voice is the signaller calling the driver. Multi-train voice communications is group calling. Trackside maintenance and shunting operations, again, voice communications. We can actually use the infrastructure for shunting operations, or we can actually use the infrastructure for maintenance teams so they can communicate during their particular activities. Banking voice is perhaps where you've got a train going up a very, very steep hill, which requires 2 locomotives, 2 drivers, and they need to talk to each other. And of course, we can do public emergency calls, 999, 112. The railway emergency call, pressing the big red button. Ground-to-ground communications, voice recording, and then voice communication on board to ground users. Now, potentially, yes, you can do all of those on a GSM-R network. So what's new? Well, we've added some new applications, some new sort of ideas, which we might want to take on board when we actually roll out Frmcs. But they are basically what we can already achieve on GSM-R. Now, data. Yes, of course, we can do data on GSM-R. But with FRMCS, we can support automatic train control, so ETCS. Automatic train operation, you could argue you can do that on a GSM-R network, but there are features in ATO which would take advantage of perhaps video, which cannot be supported on a GSM-R network. We've got data communications for possession management. So maintenance teams could potentially take control of a section of line for maintenance reasons. There's also a trackside maintenance warning facility whereby those maintenance teams can be warned about an approaching train to make sure they're out of the way. We have the ability to remote control engines. We can move them remotely using the FRMCS radio system. Data recording, on-train safety device. Well, we have one of those already. It's the driver safety device, sometimes referred to as the dead man switch. The working alone facility could be used to supervise workers, maintenance operatives, whereby if they are incapacitated, if they have a fall, maybe some kind of inertia detection system within a handheld device could report the problem to a manager, and using GPS information as well, we can then send assistance to that worker. Train integrity monitoring is something which potentially could support ETCS at level 3, because it will actually allow us to check that the train has not become decoupled and we've left a carriage behind on the line somewhere. So train integrity monitoring is one of the things which will be required for ETCS at level 3, and potentially FRMCS can do that. We've also got data communication for shunting operations. So rather than using simply voice, it might be quicker, faster, more efficient to use data. The virtual coupling is another feature which we could use with ETCS. The idea with virtual coupling is if you have 2 trains under the control of ETCS and the leading train is slowing down, that leading train could actually pass braking information to the following train, so it can then recalculate its braking curves and slow the train down as required. But potentially it will actually allow us to actually have a much shorter head rate, and therefore trains could travel closer together, and that will actually maximize capacity on the line. So virtual coupling allows trains to talk to each other with regard to braking and speed operations. We could even remotely control the parking of trains. And the on-train wireless backbone, well, when we actually connect carriages together, it involves lots of cabling. Cabling over time becomes faulty. Replace all that cabling and use radio. Use a wireless backbone system. And the critical advisory messaging is maybe a voice system or possibly a data system where we can actually have predefined messages, or they can be live messages, perhaps advising drivers about speed changes, how to proceed in an emergency, possibly instructions about how to operate at a level crossing. And the ability to monitor critical infrastructure, such as level crossing. So if there are any issues with the level crossing system, they can be reported via FRMCS. And that's something which we cannot support on GSM-R would be video, because GSM-R just does not have the bandwidth. It doesn't have the ability to carry the huge bit rates that we would need for video operations. So video will have a major part to play in automatic train operation, automatic train control. The critical real-time video is we could perhaps stream live video through to the actual control center. It would be helpful for train parking operations, trackside maintenance, and the non-critical real-time video would be supporting security, monitoring passengers on trains and station platforms. So yeah, a lot of the applications can be supported on GSM-R. Many can't, such as the video applications, but something which GSM-R is going to lose out with is capacity. We don't have the capacity with only 19 radio channels and the TDMA technology we use for GSM-R. The replacement, the successor for GSM-R, has potentially going to offer us a lot more capacity so we can support all of these applications. Then we have the performance communication applications, of which I've counted 20. So multi-train voice communications allows drivers to speak to one another in a group call. On-train voice communications allows the driver to speak to other train operatives on the same train. We've got line-side telephony, public address on trains, station public address. Yes, I realize we already have these things, but they actually use their own systems. We use copper wire or fiber optic and such like. Why not replace all of that sort of legacy architecture, infrastructure, and use radio, use FRMCS to support those applications? That will lead on to the communications at stations and depots, on-train telemetry communications. So we can actually have engine diagnostics reported from the train to a trackside system. We've got infrastructure telemetry communications, so things like axle counters and AC circuits and DC circuits used to monitor whether a particular block section is occupied or not. Well, instead of using copper or fiber optic to do that operation for that communications, why not use FRMCS? We've got the monitoring and control of non-critical infrastructure. We've got non-critical real-time video, wireless on-train data communications for train staff. So train staff can get access to the Wi-Fi, to the public internet. And we can also apply that to the railway staff on platforms as well. So we don't necessarily have to use Wi-Fi. Again, we can actually use FRMCS to provide data communications for staff members. The train driver advisory allows us to improve train performance, ensure trains run according to the timetable. Yeah, I realize there are systems out there today that will do that, but we can actually now deliver that information using FRMCS. Train departure communications, ensuring that passengers get on board the train safely and alight the train safely. Messaging services, transfer of data. The record and broadcast of information is very much like the voice broadcast service we had in GSM-R. And all the CCTV footage that's been collected on board the train needs to be transferred to a remote system. Perhaps we can do that when the train arrives at a station. We can also support real-time video calls. And what about augmented reality data communications? So you're a maintenance engineer with your camera, looking at a particular piece of equipment, and you want some assistance. You want to know what a particular switch does, what a particular light means, what a particular code represents. Well, it's possible to actually superimpose data onto that picture, augmented reality. And these types of things can actually improve, those maintenance tasks. And the business communications applications, well, there's only 4 specified in the URS. Information help points for the public, so the public can get access to timetable information, passenger information. We've got an emergency help point for the public, so should an emergency take place at a station, for example, members of the public can use that system to get guidance as to what to do. And then we've got wireless internet for on-train passengers and wireless internet for passengers on platforms. So instead of using Wi-Fi, why not use the alternative technology? Why not use FRMCS? So we can support all of those applications with potentially one technology. Now, interestingly, the UIC state that FRMCS is technology agnostic. So it could be 4G LTE, it could be 5G, it could be Wi-Fi, it could be satellite. In fact, it could be a mix of all 3 or 4. You might think, well, why satellite? Well, satellite might be of interest if you are providing communications in the Australian outback, where there are vast spaces where it's not practical to put terrestrial base stations. Wi-Fi might be useful at stations. We might want to offload our CCTV footage using a Wi-Fi connection rather than another type of connection. We mentioned 4G LTE because it was initially thought that 4G LTE would be the technology of choice. Because when the URS was first published back in 2012, we didn't actually have 5G at that time. It didn't exist. And so over the years that the URS has been sort of evolving, resulting in the latest version in 2020, 4G LTE has matured and it incorporates lots of the mission critical features that we'd like to take advantage of in a railway network. But of course, in that time, and fairly recently, 5G has emerged. So potentially maybe 5G will be the better choice rather than going for an older technology. But all those technologies are radio technologies. The other thing to note is with FRMCS is it is a client server model that we are using. So we'll be running an application on a client device. It might be the cab radio as we know it, but this will be a smart device running an application, supporting voice communication perhaps. And we'll be talking to a server in the network, and that server will be responsible for maybe replicating that voice so we can set up point to multi-point connections. So the server in the network will communicate with all of the other people in that particular group call. Now, this client server model is nothing new. We use that, for example, with ETCS. With ECTS, we have on board the train a computer, the European Vital Computer. And trackside, we have a device referred to as the Radio Block Center. So the EVC and the RBC talk to one another, currently via circuit switch GSM or perhaps GPRS, but it's a client server model. And we can apply the same to automatic train operation, voice messaging, real-time video, and also non-real-time video as well. So I've stolen this diagram from one of our 5G courses, and I think it's sort of widely accepted that the technology we will choose for FRMCS is 5G. But as mentioned, when the FRMCS was being developed, the only technology we had at that time was in fact 4G. So some of the actual concepts, some of the ideas, some of the things which I talked about still refer to 4G LTE as a potential candidate. So this diagram where it says drivers for 5G is not drivers for the railway industry, it's really for the commercial users. And I just wanted to use this diagram to make a few points. So top left-hand corner, it suggests one of the reasons why 5G is important for the commercial operators is because there has been a flattening of broadband revenues. Okay, mobile subscribers, customers are constantly looking for the best deal, and that's driving prices down, and therefore operators can't make as much money. So they want to introduce some new features, new technologies that can actually give them the cutting edge and perhaps be able to actually generate other revenue streams. So as a consequence, we have these new use cases. So extreme left-hand side, new use cases with different requirements, some requirements which perhaps cannot be supported on a 4G LTE network. And if we want to offer bigger bit rates, we need more radio spectrum. And this is where we have a bit of an issue with FRMCS. And we'll talk about those issues very, very shortly. But generally speaking, in the commercial world, if we want to offer bigger bit rates to mobile subscribers, we are going to have to go higher and higher into the radio spectrum. And that's what we are doing. 5G also provides very low latency communications. Latency is the delay that your packets incur as they travel through the network. And if we want to support real-time applications, critical applications, which apply directly to the railway environment, we do need low latency communications. Higher efficiency, higher energy efficiency. Yeah, we're going green. Everybody is going green. We're all conscious of the climate. So we need to minimize the amount of power we're using to transmit our bits of data. And 5G also removes the need for backwards compatibility. Okay, 5G is backwards compatible with 4G LTE, but it's not backwards compatible with GSM or UMTS. So that then poses a small challenge for us, because in the early years, we are going to have GSM-R running in parallel with 4G or 5G. And if there's no interworking between 5G and GSM-R, clearly this needs to be addressed. Now, these are the 3GPP, the third generation partnership project use cases. And it's a curious diagram. Extending towards the right-hand side of the diagram, it mentions the enhanced mobile broadband. Well, LTE was a mobile broadband network. 5G is an enhanced mobile broadband network because it will provide data at much, much bigger bit rates than ever before. And included in the examples is, ultra high definition television. Well, we might want to do that on a railway. We certainly want to support communications on trains. So in other words, we're taking into account speed, and 5G can operate with terminals moving at speeds of up to 500 kilometers per hour. So that should, include our high-speed trains. And as I've already mentioned, we've got augmented reality and possible virtual reality. Going anti-clockwise round, we've got critical communications. Critical communications, commonly called ultra-reliable, low latency communications. So if we're using radio to pass, ETCS messages to control the movement of trains, then those instructions need to be delivered with the highest level of reliability. And we also need to minimize latency as well, potentially, especially if we're perhaps using, this technology for, parking of trains or the remote control of trains. Moving around, we've got network operations, and we will mention network slicing because that is potentially a way forward, but we'll talk about that in just a few moments. And then towards the left-hand side, we have massive machine type communications. Well, we have machine type communications in 4G LTE, but now it's massive, it's bigger. We are looking at perhaps 1 million devices per square kilometer. And of course, in a railway system, we've got lots of devices out there, and we've got trackside circuits, train occupancy detection circuits. We could use 5G to provide that communication between those remote devices. So it's a Internet of Things technology. And the bottom one, the EV2X. Well, V2X is Vehicle to Everything Communications, and E stands for enhanced. So enhanced vehicle to everything communications will allow us to pass information between trains. So I've already mentioned things like the train integrity checking. We've also mentioned the ability for trains to talk to each other to actually control their speeds and calculate braking curves. So trains talking to trains is all encompassed in this enhanced vehicle to everything communications. So there are many, many use cases that are applicable directly to the railway industry. I just want to make a couple of points with this diagram. Right at the top, there's a horrible abbreviation, OFDMA, orthogonal frequency division multiple access. Well, that's the radio technology we're going to use on the air interface. It replaces TDMA that we had in GSM. We also use it in 4G LTE. It's just a continuation in 5G. But going around the circle anti-clockwise, we will be using higher radio frequencies in the commercial 5G network. We'll be using much more clever antennas, antenna arrays, smart antennas, beamforming antennas. It says close into working with LTE. Yeah, 5G networks today are not purely 5G. They actually work in parallel with 4G. So it's a hybrid system, sometimes referred to as a non-standalone architecture. But eventually we will see standalone architectures becoming available. 5G is also designed to interwork with Wi-Fi. So if we're going to use 5G for FRMCS, we can easily interconnect our Wi-Fi devices as well. But as mentioned, there is no support for 2G or 3G. And we need that support. We need to actually interwork with GSM-R if we are going to go through our migration phase and run the two systems in parallel. I'm not going to get involved in network function virtualization or software-defined networking. That's something we can discuss on other courses. But network slicing is an interesting one because potentially you don't need to build an FRMCS network. You could basically buy a slice of a commercial operator's 5G network, and that slice is dedicated to railway communications. Of course, it's also going to be shared by the general public as well, but you've actually got your own network slice, and the commercial operator can then take care of the actual communications on behalf of the railway operators. So in theory, we don't need to worry about replacing GSM-R, but that's going to be a very, very contentious statement to make. The problem that we potentially have with FRMCS is the lack of spectrum. This slide illustrates the current spectrum that we use for GSM-R. It's referred to as the Harmonized Spectrum because it's available in all European countries. On the right-hand side, we've actually got the downlink spectrum, which extends from 921 megahertz to 925 megahertz. In other words, it's a 4 megahertz block. So that's used by the base stations to transfer information down to the trains. And on the left-hand side, you've got the uplink spectrum, again, 4 megahertz wide, 876 to 880 megahertz. And the radio people amongst you will know that we then divide that spectrum into channels. Channel spacing is 200 kilohertz. So that gives us 19 channels, which are referred to as absolute radio frequency channel numbers. And indeed, the channels are numbered 955 to 973. We don't have enough channels. And this is going to be a bit of a problem when we start to roll out ETCS, because we will quickly run out of capacity if we want to support ETCS. We could opt for GPRS. Using GPRS, using the same channels, can potentially give us a 4-fold increase of capacity. But still, in a busy area, in a busy railway location, we are still potentially going to be really, really tight for capacity. Now, in some European countries, there is a little bit of extra spectrum available. It's referred to the extended railway GSM spectrum. It's also referred to as non-harmonized because it's not available in all European countries. So it is available in Germany, for example, but it's not available here in the UK. Now, this additional spectrum is 3 megahertz wide. So we have an additional 3 megahertz at the bottom of the downlink spectrum, and that's paired with 3 megahertz in the uplink. And if we wish, we could actually then use that 3 megahertz to create an additional 15 ARFCNs, which we could use then for GSM-R. The reason why that spectrum is not available in many countries is because it's actually used by short-range devices. The short-range device community are hanging on to that spectrum for dear life. It's used for sort of hearing aid devices. It's used for meter reading applications. It's actually also used for radar systems, which are used in the UK in basically to detect whether a level crossing is actually obstructed or not. So I guess we're sort of our own worst enemy in that we're actually using the spectrum for railway applications. But because of the SRD community, that spectrum is not available in all European countries. If it was available, then potentially what we could do is actually locate a 1.4 megahertz FRMCS channel. Okay, now the technology we are using here is LTE. Okay, the reason for that is because, as I mentioned, when we first start to think about FRMCS, 5G didn't exist, LTE did exist, and there is a 1.4 megahertz channel available in LTE. So we could actually locate that at the bottom of the GSM-R spectrum. We would need a 200 kilohertz guard band to control the interference between, LTE and GSM-R. So those two technologies could coexist, and we can actually run the two systems in parallel. And eventually, then over time, what we can then do is basically, decommission our GSM-R sites and eventually turn the entire spectrum into 4G or possibly even 5G spectrum. Now, helping along the way was a decision made by the ECC, decision 2002. They have decided that an extra 1.6 megahertz of spectrum should be made available at the bottom of the existing harmonized GSM spectrum. So in other words, the SRD community are going to have to move a little bit, and that will then free up 1.6 megahertz of spectrum. And clearly you could fit a 1.4 megahertz, excuse me, a 1.4 megahertz LTE channel into that space, and also have your 200 kilohertz guard band separating LTE from GSM-R. Or we could actually use that spectrum and create an additional 8 ARFCNs for GSM-R if we wish. Now, the problem with that is that there isn't a 1.4 megahertz channel available in 5G. So we couldn't actually put a 5G system into this 2002 spectrum. It's just not wide enough. The smallest channel bandwidth that's available in 5G is 5 megahertz. So I guess if you were to combine the 1.6 megs with the GSM-R spectrum, that would give us 5.6 megahertz. Okay, so you could actually have a single 5 megahertz 5G channel, and then just a little bit of capacity for a few GSM-R base stations. But that would take a lot of careful planning to actually do that. What helps is in the same decision that the ECC made, they identified another block of spectrum that could be used for FRMCS. This is at 1900 megahertz. 3GPP referred to this as band 33. And it's the spectrum in the diagram on the left-hand side, labeled TDD, time division duplexing. This spectrum was originally set aside for 3G UMTS, and the spectrum is specifically between 1900 and 1920. That's what the commercial users were licensed to use. Time division duplexing means that we would need to use one frequency for the uplink and the downlink on a timeshare basis. So if the base station is transmitting, the mobiles listen. When the base station stops transmitting, the mobiles can transmit uplink, but on the same radio channel. None of the operators in the UK ever deployed UMTS working in that TDD spectrum. So it's been sat there for well over 20 years, unused. And the spectrum which has been identified by the ECC is specifically between 1900 and 1910 megahertz. So it's a 10 megahertz block of spectrum, and we could quite easily fit a 10 megahertz 5G radio channel in there. Small snagette, small problem here in the UK, in that spectrum that ECC have indicated could be used for railway is actually currently licensed to EE, and they're using that 10 megahertz of spectrum to support ESN. ESN is the Emergency Services Network, which interestingly is a mission critical network using LTE. So they're actually using this spectrum as an LTE TDD channel, which is 10 megahertz wide. So the challenges we face. Well, first of all, the functional requirement specification and the system requirement specification are not in the public domain as of the 6th of October when I put the slide together. We are now on the 9th of November, and I still haven't seen an FRS or an SRS yet. We then have the testing and validation. Well, as we mentioned, the project 5G rail is is taking care of that. It's planned, but of course we're awaiting the FRS and the SRS. In terms of equipment supply, well, we can't build equipment really without any standards to actually work from. And potentially we are going to be using 3GPP, 5G technology. It will be release 16. But the 5G standards don't currently include the mission critical applications. Mission critical push to talk, mission critical video, mission critical data, they've all been standardized for LTE, but they have not yet filtered over into 5G. So we're still waiting for that. And of course, as we've seen, the spectrum is a bit of an issue. We don't have enough of it to support 5G. Maybe we can persuade 3GPP to develop a 1.4 megahertz 5G channel. Is that a possibility? So the spectrum is sort of partially agreed, and time, well, there's never enough. Okay, that's the end of my little chat about FRMCS. I can hand it back to Paul.
Yeah, thanks, Les. Very interesting. Hope everybody enjoyed that. Yeah, just to let you know that I'll be sending a recording of this webinar out to everyone that registered within the next day or so, so look out for that. And if you're interested in any further training on railway communications, and we have some courses covering GSM-R, ERMTS and FRMCS, so please go to our website, raycastle.com, for more information on those. But yeah, just like to thank you all for attending. As I say, Les, thanks a lot. Very interesting session.